Welcome to solverfy.
Question 56 is a weak acid, strong base titration. For weak acid, strong base titrations, we need to carry out a weak acid calculation at the at the initial point, buffer solution calculations using the Henderson-Hasselbalch equation, pre-equivalence, a weak base calculation at the equivalence point, and then an excess strong base calculation post-equivalence. So let's get started. For the first one, we have 0 milliliters of strong base that has been added. If we have 0 milliliters of strong base that has been added, then all we have is the weak acid solution that is present. If all we have is the weak acid solution, we'll carry out a weak acid pH calculation, where the pH can be determined by taking the negative log of the hydronium concentration. And the hydronium concentration is simply equal to the square root of the Ka value, which was given to us at 1.54 times 10 to the negative 5, multiplied by the concentration of the weak acid, which was given to us at 0.1 molar. So this right here gives us our hydroxide concentration, our hydronium concentration. This right here gives us our hydronium concentration. If we take the negative log of that, we'll get our pH, and our pH is 2.91. For all the other calculations, we need to know where the equivalence point is. If we have 20 milliliters of 0.1 molar butanoic acid, and we are titrating it with 0.1 molar sodium hydroxide, because the concentrations are the same and the stoichiometry is 1:1, then the volumes will be the same. So 20 milliliters of sodium hydroxide is what is required to neutralize 20 milliliters of 0.1 molar butanoic acid. So 10 milliliters is halfway to the equivalence point. Many of you might recognize that the pH for a weak acid strong base titration at the half equivalence point is equal to pKa. If you didn't recognize that, you would still know that pre-equivalence is a buffer solution and requires the Henderson-Hasselbalch equation. So that's what I've done here, is pH will be equal to pKa, the negative log of the Ka value, plus the log of the moles of base over the moles of acid. This is the Henderson-Hasselbalch equation. How will we calculate the moles of base? The moles of weak base formed will be equal to the moles of strong base added. The moles of strong base added is simply equal to the volume of strong base, 10 milliliters or 0.01 liters, multiplied by the molarity at 0.1 molar. We then divide this by the moles of weak acid that's still left in solution. That will be equal to the volume of weak acid we started with, which is 20 milliliters or 0.02 liters, multiplied by the molarity at 0.1 molar. Those moles will decrease by the moles of strong base added. The moles of strong base added again will be equal to what we had up here in the numerator. We then carry out this calculation to get a pH of 4.81, which is, because this ends up going to 0, simply equal to pKa. Now for the next one at 15 milliliters, we are still pre-equivalence, so we still have a buffer solution and we will still use the Henderson-Hasselbalch equation. It'll take on a format very similar to what we did in part B, where pH is going to be equal to pKa plus the log of the moles of base over the moles of acid. The moles of acid that we will have left will be equal to the moles of acid we start with, which is the full 20 milliliters or 0.02 liters multiplied by the concentration at 0.1 molar, minus the moles that reacted, which will correspond to the moles of strong base added, 15 milliliters or 0.015 liters multiplied by its concentration of 0.1 molar. That will also be equal to the moles of weak base formed. Essentially, the moles of strong base added is equal to the moles of weak base formed. That will give us a pH of 5.29. And as we expect, as we are adding the strong base, we should see, with each subsequent calculation, an increase in pH, which we are seeing. This is one way to verify your answers. Now we go to Part D. Part D is 19 milliliters, again still pre-equivalence, so it'll be a calculation very similar to what we had before. The only difference is now the volume of strong base added, which in this case is going to be equal to the 0.019 liters, or the 19 milliliters. And then up here we will also have the volume of strong base added, which will correspond to, when multiplied by the molarity, the moles of weak base formed. And we get a pH of 6.09. For the last one, we are just before the equivalence point at 19.95 milliliters. So we still have a buffer solution. We will still use the Henderson-Hasselbalch equation. So again, pH equals pKa plus the log of, in our denominator, it'll be the moles of weak acid that has not yet reacted, which is the moles of weak acid we start with, minus the moles of weak acid that reacted, which is equal to the moles of strong base added, namely 19.95 milliliters, or 0.01995 liters. This then is also equal to the moles of weak base formed, namely the 19.95 milliliters, or 0.01995 liters, multiplied by the molarity. This then gives us a pH of 7.41, and we are still seeing an increase in pH, as we should. Now, once we reach the equivalence point, 20 milliliters, what we have done is converted all of the weak acid into weak base. So all we have in solution is weak base. We can solve for the hydroxide concentration by doing a weak base calculation. A weak base calculation is the hydroxide concentration will be equal to the square root of Kb. We don't have Kb, but we do have Ka. If we divide Ka into Kw, this is our Kb. So hydroxide is equal to the square root of Kb multiplied by the concentration of the weak base. Well, how will we get the concentration of the weak base? Every mole of weak acid has now become weak base. So we'll take the volume times the molarity of the weak acid we started with to get the moles of weak base we now have, and then divide it by the new volume. The new volume is 40 milliliters, or 0.04 liters. So hydroxide will be equal to the square root of Kb multiplied by the concentration of the weak base, and we get 5.70 times 10 to the negative 6. The pH will then be equal to the negative log of the hydronium concentration, and the hydronium concentration will be equal to the hydroxide concentration divided into Kw, and we get a pH of 8.76. Now for Part G, we are just past the equivalence point at 20.05 milliliters, so we have excess strong base in solution. The excess strong base in solution can be used to calculate the excess hydroxide concentration. So pH will be equal to the negative log of the hydronium concentration, where the hydronium concentration is the hydroxide concentration divided into Kw. So pH equals negative log of the hydronium concentration, which is hydroxide divided into Kw. How do we get the hydroxide concentration? The hydroxide concentration will be equal to the total amount of strong base, sodium hydroxide, we've added, minus the moles of strong base that reacted, which will be equal to the moles of weak acid we started with, divided by the new volume. So all of this down here is concentration of hydroxide. Divide that into Kw to get hydronium, take the negative log to get our pH, and we get 10.10. For the last one, we'll do a calculation very similar to what we just did, but in this case we are at 25 milliliters, so we will have the total volume multiplied by the concentration of the strong base added minus the moles that reacted, which will be the moles of weak acid we started with, multiplied by its concentration, divided by the new volume, which is now 45 milliliters or 0.045 liters, and we get a pH of 12.05.